Hello, everyone. In this final video for section 5.6, we're just going to look at example 3, followed by some notes and observations. So here we have let f of x be the function 1 over x, and we're looking at the interval from 1 to 2 of 1 over x dx. And we want to write what we think this value is here. So we can actually do this, right? We can compute this integral. So we see that 1 over x, the antiderivative is ln of x. So we evaluate that at x equals 1 and 2 and subtract. So we get ln of 2 minus ln of 1. ln of 1 is just 0 because e to what power gives me 1? Well, that would be 0. So this is just ln of 2, which if we plug that into a calculator, we get that the ln of 2 is about equal to, it's a repeating decimal or non-repeating decimal forever, but it's 0.69314711806, etc. All right, so there is the actual exact value of the integral. So now let's take a look at this table that sorts out for us the trapezoid and midpoint approximations. So we can make some observations about this table. So what do we observe about our approximations as we use more and more rectangles? Well, what we should notice is that as we use more and more rectangles, these approximations get closer and closer to our exact answer. And so then we just have some notes and observations about how close we get. So first, it says each time n is increased by a factor of 10, we gain about how many decimal places of accuracy in both rules. So as we go from 1 to 10, we get 0 or 1 decimal place of accuracy to 2 or about 3. When we go from 10 to 100, we gain, it looks like, another couple of decimal places. When we do another to 100 to 1,000, we get even more decimal places. But each time we get about 2 to 3 decimal places. So we can say 2 decimal places of accuracy more. And then here we have the trapezoid rule underestimates this integral by about blank the amount by which the midpoint rule overestimates the integral. So here we need to look at the errors of each. So how do these errors of these two different approaches differ? We see that the error here in the trapezoid is an underestimate about twice the size of the overestimate coming from the midpoint rule. And we see that this follows as we go all the way down. So what that means is that the trapezoid rule underestimates the integral by about twice the amount by which the midpoint rule overestimates this integral. So this leads to a new rule called Simpson's rule, which is basically just using the midpoint and trapezoid rule together. So Simpson's rule says how you should approximate the integral is to take 2 of the midpoint approximation, add that to 1 of the trapezoid, and then divide by 3. So essentially, we're looking at an average of 2 midpoints and a trapezoid. Average. So Simpson's rule is not necessarily a separate rule, but it's a way of using midpoint and trapezoid approximation to approximate the integral. And it's because of this relationship that we're seeing in the errors in general. So the midpoint, again, overestimates about twice as much, or rather the underestimate of the trapezoid is about twice as much as the overestimate of the midpoint. So accumulating 2 of the midpoints sort of outdoes the trapezoid. So if we add up 2 of these and 1 trapezoid, divide by 3, that gives us a fairly good approximation. Okay, so when Sn is used to approximate the integral, it can be shown that each time n increases by a factor of 10, we gain about 4 decimal places of accuracy. So this just shows that the Simpson rule needs less rectangles overall in order to make a more accurate estimate. Okay, so again, you won't need to memorize any of these notes. This is just a good way of taking a step back, looking at our approximations, and figuring out some best practices and best methods for getting the best approximation of our integral. All right, thanks so much for watching. Keep up the hard work.